Greetings. Let's talk about angular momentum. So to get started, let's take our kind of simple way of doing this. So we had linear momentum. Linear momentum, ignore that wasn't there. We defined as the mass of an object times its velocity. So the simplest way we could think of angular momentum would be to do our kind of usual substitutions. And so when we do linear to angular substitutions, m goes to I, the rotational inertia, v goes to omega, the angular velocity, and p, our linear momentum, will go to L, our angular momentum. Strictly speaking, these are vectors, but you almost always will ignore that. Now, when we're thinking of angular momentum in this context, I omega, we'll usually think of something like a top. And so this top is spinning. Ooh, can't really tell if that's spinning at all. Spinning with some angular velocity, omega, and it has some rotational inertia I, and so the momentum of that is I omega. You can think of it requires some kind of rotational impulse, and I really should know if there's a word for rotational impulse, and I don't remember if there is a word for rotational impulse, but basically the amount of effort you have to expend to get a top spinning depends on how fast you want to spin it and how bulky it is. The thinner and more compact it is, the smaller I gets, the easier it is to spin. Brief reminder, I we can think of as the sum of mr squared over kind of all the components, or we can think of it as the integral of dm r squared over the whole volume. But basically it looks like how spread out the mass is. The more massive it is, the bigger I is. The more spread out it is, the greater r is for any chunk of mass, the bigger I is. But let's table that for a second. Let's take a slightly different approach. We're going to define angular momentum in this manner. It's going to be the cross product of r and p. Thinking of this in a similar way to how we define torque as the cross product of r and f. And so in this kind of case, we're saying you have an object of mass m moving with speed v, so it has some linear momentum, about a point p. So this doesn't have to be an object moving in a circle. That's an important change here. It's simply an object moving about a point. That's what's going to give us angular momentum. The about a point is obnoxious in a way, because it means that even though this thing has a definite linear momentum, has a definite mass m, definite speed v, or definite velocity v, if I were to pick a different point p, should give me a different, r, locating it from that point, I would have a totally different angular momentum. Angular momentum depends on how you look at it, to some extent. Kind of annoying, but, go with it. Now, just to briefly try to motivate this, consider our definition of not our definition, just Newton's second law. I'm really bad at remembering my vectors. F net equals dp dt. So what I want to do is cross r into both sides of this. So I have r cross F net and r cross dp dt. A little bit of hand waving. This, recall, is our definition of torque. So that's a simple change. And then I'm going to put r into my derivative. Just going to go with that. Strictly speaking, you wind up with, you can have something that's changing r and changing p. And again, just like when we talked about the definition of momentum, you can have something that's changing mass and changing velocity, both require a force. Same idea here. And so this is going to motivate us defining this r cross p as L, our angular momentum. And that's kind of, what we would expect. We have our rotational version of Newton's second law replaces the net force by the net torque, replaces the linear momentum by the angular momentum. So you may notice that we've switched from an uppercase L to a lowercase l. You might be wondering, what's the deal with that? So, we have lowercase l for angular momentum as r cross p, uppercase L as I omega. So how do we reconcile these? Well, what we're going to wind up doing is defining this uppercase L really as kind of L total, the total angular momentum. We can think of it as built up as, the sum of the angular momenta of things in the system. again, to recall the similar case, we said that kind of capital P, the total linear momentum, was the sum of the individual linear momenta. Now, the reason this is going to be useful for us is because it's going to let us shift between these two definitions. So consider the simplest case, object traveling in a circle at speed v. So if we were to do that, well, this would be our angular momentum, mr cross v. If it's in a circle, when I go to do this, I take the cross product, I get mrv sine theta. The angle between r and v, if I'm traveling in a circle, so, that's not really a straight line. Here is r, here is v. These are always perpendicular in a circle. Remember back to uniform circular motion. It's more or less what we're describing here. So sine of 90 is 1, so L is mrv. The direction of it is a little weird. So you'll notice that I have here a vector. This should be a vector, but I haven't really indicated the direction. As I have set this up, the angular momentum is into the page. It is determined by the right-hand rule. And so if I put my right hand in the direction of r, with my fingers, like if I make just a straight knife-ish kind of, you're trying to give someone a high five. Turns out it's really hard to do this when I'm gesturing at my hand and you can't see my hand. But you just kind of stick your arm out straight, fingers out straight, and point that in the direction of r, and then curl your fingers in the direction of v. So I'm sticking my arm out to the right. I'm curling my fingers to the back. The direction of my thumb will be the direction of the cross product. So r cross v, r points to the right, v points down the page, L will point into the page, which is customarily then minus k hat. But usually it will suffice to say into the page. Another way to think about this is that you can kind of do a reverse version of the right-hand rule. You know that this is going around the circle clockwise. So if I took my right hand and curl my fingers in a clockwise manner, my thumb points in the direction of L, points down, points into the page. All right, so we got the direction sorted out, but let's take a look further at this for a second. We can manipulate it a little more. I'm going to arbitrarily multiply by r and divide by r. Well, not quite so arbitrarily, because if we look at this, that's going to give me I and omega. And so in this case, we can see, at least in the simple case, that these definitions are actually equivalent. We can move between them somewhat freely if we wanted to. The benefit will generally be that we want to use this definition for point objects or point-like objects. So this is going to mostly be orbits or things not really going in a circle. I should have found a shorter way to say that. Whereas this definition, in terms of I omega, will be useful mostly for rigid bodies. So things that have a well-defined I, moving in, circular paths, basically. Didn't think that through all the way. Now, this said, there are going to be moments where you can basically use either of them. Sometimes it will be a matter of taste. Sometimes it's a matter of just, whichever one clicks to you. They are equivalent definitions. It's just that often, one makes more sense to use than the other. Basically, it comes down to, is it easier to talk about R or is it easier to talk about I? Now, there's one other thing about this, and that's, shockingly enough, conservation of angular momentum. Just like linear momentum, in the absence of a net external torque, angular momentum will be conserved. So the initial angular momentum of a system will be equal to the final angular momentum of a system. And now that you've had a good 20 seconds to stare at this wonderful stick figure, let's talk about what's going on here. So consider for a second ice skater. You can tell because our ice skater is wearing ice skates. I think that's a foot over here, and this is probably a foot. I don't know. You may have to use your imagination. But, I'm sure that we have all seen this. If you haven't seen an ice skater before, you should probably pause this and go Google, Olympic figure skating. But you can have a case where a figure skater is crouched low, arms and legs extended and spinning, and then gradually pulls the leg up until it's very compact and still also spinning. So if we consider this for a second from an angular momentum perspective, this is going to be best taken care of. So think for a second. Is this best done with L equals MRV or L equals I omega? Give it a moment's thought, and once you have a decision, if you haven't made it already, you can keep going, but think on it. The best way, it turns out, in this case, is going to be I omega, because we're basically looking at a rigid body, not a point. So what we're saying here is that the initial I, the initial omega, will equal the final I times the final omega. Because it turns out, as the skater lifts her leg and compacts herself or himself, not only does the skater's rotational inertia change, but the skater's rotational velocity changes. In this case, I is much larger. The mass is spread out over a wider radius. So omega is going to be smaller. As the leg is pulled up and the body is pulled in to make it a more narrower frame, the rotational inertia decreases, the angular velocity increases. We're going to look at in class some examples of this also, involving spinning around and hoops and wheels and weights, so we can try to get a better sense of it. So anyway, recapping. We're moving now linear momentum to angular momentum. Same basic ideas, we can just do our variable swaps. And what we're talking about is more or less, what it means to be in motion about a point, whether you're spinning about a point like a top or orbiting about a point. And so, in either case, we can think of kind of orbiting, we can think of kind of spinning. Both cases involve some form of angular momentum.